Taylor series. One of these topics that when you're learning for the first time seems completely strange and pointless because you're taking a perfectly good function like, I don't know, exponential or sine, and you're replacing it with a whole lot of other functions that are a lot more complicated and have a big sum formula, and what was wrong with our function in the first place? Well, it turns out there are actually some pretty good reasons why we might want to learn about Taylor series, and a really big one is the idea of numerical methods. So when we have something in the real world that we want to, for example, simulate, it might be a racing car aerodynamics, or it might be the spread of a disease, or it might be population growth of something or other, and we usually use differential equations, and to solve these on a computer, we use numerical methods. Taylor series are an important tool, just one of the many uses of them, for developing these methods. So there are reasons why we want to approximate with nice things like polynomials, but at this level, we're kind of just getting to grips with how the method works and kind of the nuts and bolts of it rather than looking too hard at applications. What are you doing?
I'm just here to provide some comfort and relief while you work on this difficult topic.
Okay, makes sense. So, all right, let's get into it with an example. So here's one. We want to calculate the Maclaurin series of cosh of x using the definition. Okay, so that maybe brings up two questions. Question number one, what is cosh of x? And question number two, what is the definition?
Yeah, okay, Mr. Guitar, that's flippin' annoying.
So cosh of x, or the hyperbolic cosine, is just, as far as we care about it, is just going to be e to the x plus e to the minus x over 2. And there's a similar function which is called hyperbolic sine, or sinh of x, and this is almost the same except there's a minus sign instead of a plus there. And one interesting property of these is that they both differentiate to each other. Okay, so let's get back to our question. We want to find the Maclaurin series, therefore, of cosh of x using the definition. So what we're going to have to do is basically find a whole lot of derivatives, because the definition of a Maclaurin series, remember, is that a function is equal to its value at 0 plus its derivative at 0 times x plus its second derivative at 0 over 2 factorial, which is just 2, times x squared, and then we just continue on. So plus the third derivative at 0 over 3 factorial times x cubed, and so on and so on. Okay, so whenever we're doing one of these things by the definition, what we're being asked to do is to find all these derivatives and find an expression for this. And we often want to write it using that fancy sigma notation at the end as well. Okay, so let's write down what we need here. Let's just go, we'll make a little table, we'll put our different derivative values. So we'll go k for our 1, 2, 3, 4, 5, etc. And then we'll go f of x, or f, the kth derivative, which we write like that, of x, and then we'll go the kth derivative of 0 and see if we can spot a pattern. Because once we've got a pattern, then we can kind of just plug the gaps in the formula and away we go. So we'll start off with k at 0, that's our sort of our first one, the nothing derivative. So f to the k of x is just going to be our function itself, which is cosh of x. And cosh of 0, if we just look at the formula over here, is going to be e to the 0, which is 1, plus another 1, which is 2, divided by 2, which is going to give us a value of 1 here. Okay, for our first derivative, f1 of x, that's the first derivative, our cosh cosh differentiates to sinh. So we take our sinh, put it in here, and when we put our sinh at 0, we go e to the 0 minus e to the 0, this is going to be 0. One thing I didn't anticipate was how hard it was going to be to say differentiate cosh and differentiate sinh. So when we want to get our second derivative, well, sinh differentiates to cosh, so we just end up back where we started. And therefore, when we put 0 in, that just is going to give us 1. And this pattern is just going to continue, so it's going to be sinh. The third derivative of our cosh function is going to be sinh, and when we put 0 in, once again it's going to be 0. So these things are just going to alternate between 1 and 0. So therefore our Maclaurin series, remember Maclaurin series is just a Taylor series where we're at 0. I haven't written down the Taylor series definition, but it's just similar to our Maclaurin series one here. So we're going to have, let's just see if we can write it out and put the terms in. Our function is going to be f of x is equal to f of 0. Yep, we got that. F of 0 is just 1 plus f prime of 0 times x, that's plus 0 times x, plus f double prime of 0 over 2 factorial times x squared. So remember that f double prime was 1, so divide that by 2 factorial times x squared, plus third derivative at 0, that's 0, over 3 factorial times x cubed, and you can kind of see that the next term is going to be plus 1 over 4 factorial. The derivative is going to be 1 again, x to the 4, and so on. So we're only going to get even terms, and they're going to look like this. All of the odd ones are going to have zeros in the front, so they're going to disappear. So we can tidy this up in a couple of steps, and then we'll see if we can write it in that summing notation. So that's going to equal 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial times x to the 4 plus etc. 1 over 6 factorial x to the 6, and so on and so on. Now let's see if we can write this down as power in a sort of nice sum form. Remember that 1 can also be written as x to the power of 0, so that would actually fit as well if we're trying to write this inside a sum. So we're going to do a sum. We want to just sum over the even numbers. So we usually start our sum off at 0 and we go off to infinity. And a nice way of ensuring that we've only got even numbers is just to use 2k as the number instead of k. So instead of trying to sort of incorporate the even numbers into this sigma notation somehow and just say k not odd, that's kind of messy, so we don't want to do that. We'll just use 2k as our index instead. So it's going to be something like 1 over 2k factorial. Okay, that's our even number, 1 over the even number factorial, times x to the power of 2k. Now sometimes you might not be quite sure if you've got especially the beginning of your series right. Like I'm quite happy that from 2 onwards this is going to be fine. Let's just check k equals 0. That will be 1 over 0 factorial. Remember 0 factorial is just defined to be 1, so that's fine, times x to the 0, which is just 1 over 1 times 1, which equals 1, which is the thing that we hoped we'd have. Okay, so we have found our Maclaurin series for cosh of x and expressed it in a nice sort of sigma notation. And also the other thing about Taylor's series is there's this idea of radius of convergence, which we're not going into in any great depth in this course, but because we know that exponential function e to the x converges for any value of x, it also, this means this function here, which is just a sum of exponentials, will also converge for all values of x. So this converges for all x, just by using our knowledge about how exponential works. All right, that's example number 1. Let's now do another one. So that's an example of finding a Maclaurin series by the definition. Now let's do an example where we're going to use our knowledge of a Maclaurin series or a Taylor series and use it to solve a problem. So here we have a limit problem. We're given the expansion for a binomial series. Binomial series is just 1 plus x to the power of k. Why is it called the binomial series? Because these things, especially if you've done any stats before, you might have met these. These are called binomial coefficients. And they're often written as n choose k. Okay, so, and the other important point is this formula here works for values of k that aren't just integers. Okay, k can actually be any real number. And it will, and this is the series that works for here. And the other thing about this series is that we basically need negative absolute value of x to be less than 1. in order for this thing to converge. Okay, so let's see if we can use this knowledge to find a limit. Now, we could approach this limit using L'Hopital's rule. In fact, let's just check that this limit actually does what we think it will. So on the top, as x goes to 0, that x is going to be 0, so it's going to be 1 minus 1 minus 0 on top, that's a 0. And on the bottom, we're going to have 0 as well. So this is an indeterminate form of the form 0 over 0. So we could apply L'Hopital's rule to solve this one. But we can also use our Taylor series knowledge to solve this a different way. So what we're going to do is we're going to take our square root of 1 plus x term, and we're going to replace it with its series, and then apply the limit and see what happens. Okay, so how is this binomial series relevant to this is also another question that might come to mind. So let's just partition that off slightly. One thing you might want to note is that 1 plus x, or the square root, sorry, of 1 plus x is just the same as 1 plus x to the 1/2. So we can actually use this expansion here. And also, as our limit is going towards 0, so this condition is also going to hold, and so we can use this series. All right, so that equals the limit as x goes to 0. Let's just put in the first few terms of this binomial series instead of the root 1 plus x and see what happens. And let's do it in a different color just to keep everything nice and distinct. So k is going to be half. So let's just fill in some terms. So square root of 1, so it's going to start with 1 plus k times x is going to be 1/2 times x. I'm just reading off my formula at the top here. Now put in the squared term, which is going to be plus k times k minus 1. So that's going to be plus 1/2. 1/2 minus 1 is negative 1/2, all divided by 2 times x squared. Plus, now let's do the third power term, 1/2 minus 1. Minus 1 again is going to give us minus 3 over 2, all divided by 3 factorial, which is 6. In fact, let's just make it 6 times x cubed. And I'm just going to, before I do too much more, just see what's actually going on here. Remember that the overall structure is we've got an x squared on the bottom, and we've also got, in fact, just move some of these pieces around a little bit, make a bit more space. You guys can go down there. I've also got to subtract off minus 1 minus 1/2 x. That's the limit I'm trying to take. And we can already see something interesting. We can see that these terms are going to cancel off with these ones. And what's left, we can divide out this x squared from every piece. And remember that our limit's going to 0. So if I were to put more terms in here, in fact, then they're just going to be something times x to the power of, e.g., 5 or 6 or 7 or 8. When we divide it by x squared, we're still going to have some x's left. And when we end up applying this limit by putting in x equals 0, those terms are going to go away. So I don't actually need to write down any more because they'll all go to 0 when we put in our x equals 0. So let's just divide out that x squared from the terms we've got. So it's equals the limit as x goes to 0. And we can do some simplification of our terms here. It's going to be 1/2 times negative 1/2 is negative 1/4, divided by 2 is negative 1/8. And the x squared is going to cancel off. That's kind of this one and this one. And then with the x cubed term, plus 1, we've got 2 negatives, so it's going to be 1/2 times 1/2 is 1/4, times 3 over 2 is 3/8. 3/8 divided by 6 is 3 over 48, which is the same as 1 over 16. And the x's, well, the x cubes are going to lose 2, so that's going to become x, and then we will just continue on. And every term beyond that point is going to have some number of x's in it. And the point of that is when I put an x equals 0 into my limit, then I will just, basically everything from here onwards is just going to be 0, and so that will equal negative 1 over 8. Now, whether or not this was easier than solving this limit by using L'Hopital's rule is another question, or a question for another day, but I think we'll call it quits here. Ka kite anō.